Hey guys, before we get started, as ever, could you do the do now questions for me, please? Pause the video here and have an attempt. And here are the answers for the do now questions. Like always, we'll be doing this live on Zoom, so if you didn't get this or have any questions, make sure you log on at the appropriate time and we can discuss any of these answers. Okay, lesson 1, week 2. So last year in term 1, we looked at the Big Bang quite extensively, and that set the scene for everything that we looked at for the rest of the year. One of the alternative theories that we didn't talk about much, or if at all, was steady state. Steady state theory was a competing theory to Big Bang, and opposite to the Big Bang theory in quite a lot of ways. And we'll see as more evidence was coming out about how the universe started, the support for steady state theory started to decline, and the support for Big Bang theory eventually being then accepted as the most likely theory became stronger over time. So we're going to take a little journey back. Some of this will be a little bit revision, but there's some new information here as well on steady state. So at the moment, the Big Bang model is what we consider to be the best fit model for explaining the deep past of the universe, but over the decades there's been several other proposed. Some that were better than others. The steady state universe was one of those theories proposed. The steady state model was proposed by 3 individuals in 1948, Herman Bondi, Thomas Gold and Fred Hoyle. Sir Fred Hoyle was an Englishman, and you may recognise his name because he believed in steady state, and he actually coined the term, he made up the term Big Bang as a kind of insult to the other competing theory, because he thought, oh well, everything just started with a Big Bang then, did it? But the Big Bang actually stuck. So yeah, Fred Hoyle started, he was being a bit sarcastic about it, but the name stuck. So what are the two theories? Well, the top theory here is the evolutionary theory, or the Big Bang theory, that density of matter decreases over time. I'll explain that in a little second. And the steady state theory describes density of matter is constant over time. So the reason it's called steady state is they basically believed that everything in the universe was constantly being created at a steady, constant, uniform rate. Okay, Big Bang suggests not really. Everything was kind of created at the start, and from that, things kind of moved out and dispersed, and there's uneven distributions of mass and matter over time. The Big Bang was originally proposed in the context of making all the elements. In the original steady state proposal, all of the heavy elements were produced in stars by burning hydrogen into helium and then combining several helium nuclei into heavier nuclei like carbon and oxygen. In general, the heavy element abundances relative to hydrogen are proportional to each other. So basically what they're saying here is there was the same amount of hydrogen, the same amount of helium, the same amount of oxygen, the same amount of carbon. Okay, you had this uniform distribution of all the elements in the same abundance at the same time. That was what the steady state proposed. So another diagram here. The Big Bang cosmology, so the Big Bang theory kind of countered that. It says that matter dilutes as the universe expands. So what you're going to find is as the universe gets bigger and bigger, there's going to be areas that don't have much in them at all. Steady state, if all the elements are proportional to one another. So for example, we have 10 hydrogen, that means there must be 10 oxygen, there must be 10 carbons, there must be 10 neons. If there has to be the same all the time, then matter must constantly be created as the universe expands to meet that theory. Okay? If everything's proportional, that means that everything has to be getting created at the same time. So that was something that would become the undoing of the steady state theory. One of the main problems. Well, we know that some stars have very little oxygen, and these usually have very little iron. So we know iron is only produced in a dying star at the end, but helium is definitely an exception to this rule. So the majority of a star's life is spent turning two hydrogen atoms into a helium atom. We know that, so there's a lot of helium that's being produced. Iron is produced right at the end, and once that happens, a star builds up an iron core, blows up in a supernova if it's a high mass star, and then it fuses all the other chemical elements. But there's not enough fuel to make the same amount of iron as there is to make helium. So what we call here as well is there's a non-zero floor to the helium abundance as the oxygen abundance goes to zero. I'll explain this better in a little second. This is shown in this plot, which shows the helium and oxygen abundances relative to hydrogen by the number of nuclei in the sun. Okay, so I'm talking a lot of jargon here. What the hell am I talking about? Okay, this graph doesn't look fantastic, but let me explain, okay? So essentially, what we're saying here is helium and oxygen, there should be this proportional relationship if matter is being created at the same time all the time. So every time there's 2 helium for every 1 oxygen, there's 4 helium for every 2 oxygen, 6, 8, 10, and so on. And if you use that logic using the steady state model, then there should be at one point in time 0 helium. But we don't find that, okay? There's a lot more helium in the universe than there is oxygen. And that is explained quite well by the Big Bang, because we expected a bunch of hydrogen and helium in the early days, and as stars formed we get a little bit more oxygen and all the other elements. Steady state suggests that all the matter was there at the same time and nothing ever changed, so that doesn't make much sense based on the evidence that we have. So the plot clearly shows that the solid line, which allows for primordial helium produced in the Big Bang, is a much better fit than the dashed line, which is the prediction of the steady state model with no primordial helium. What is primordial? So remember in the Big Bang, I said that there was space, time, energy, matter, STEM. We had SWIG, the 4 fundamental forces, strong, weak nuclear force, electromagnetism, and gravity. And we said once the universe cooled down below 3000 degrees, atoms formed, and the first atoms to form were the simplest. We had mainly hydrogen and a bit of helium. So that hydrogen and helium were the primordial atoms. They were the first ever atoms, and there was more of them because they were so simple than oxygen, which needs fusion through a star, iron, which definitely needs fusion through a star. So steady state didn't really allow for the abundance. It couldn't explain why we have so much hydrogen and helium in the universe, but the Big Bang could. The Big Bang theory suggests, well, there's going to be more hydrogen and helium because they were created in this cataclysmic event right at the beginning. So, primordial, just to make sure we know what that means, primordial means existing at or from the beginning of time. It's from late Latin, primordialis, first of all, or original. From Latin, primordium, a beginning, the beginning, origin, commencement. And from primus, first. So think of primary school, it's the first school you go to. So primordial is the first order, as it were. So when we talk about primordial hydrogen and helium, we're talking about the hydrogen and helium that was there right at the beginning of the Big Bang. Okay? So steady state versus Big Bang. The discovery of another bit of evidence, the cosmic background radiation, came later and completed the death of steady state. So this was really the final nail in the coffin for steady state. So I've got an extra word in there. Cosmic background radiation we've heard of. Cosmic background black body radiation is just another layer terminology that we use to describe it. Okay, so the universe now is not producing a black body. So remember when we thought of the plasma universe, it trapped photons of light, and that was because it was not isothermal. There wasn't the temperature didn't stay the same. Okay, the temperature as the universe was expanding, we know that it was getting cooler and cooler. And when it got below that threshold temperature, again, 3000 degrees, when it got below 3000 degrees and the atoms started to form, remember the plasma universe ended and the photons of light escaped, and they went out to all areas of the universe, and that became the cosmic background radiation. So you have a very distinct event happening here. You have the universe was turning from something that was opaque. Okay, so opaque is, imagine you had a bit of glass that was dirty, for example. You had a bit of glass and it was covered in paints or something. You sometimes see that in shops when they're renovating, they don't want you to see in. They cover it in sort of paint and you can't see in. Then suddenly you wipe all that clean and you can see through the window. It becomes transparent. And this is kind of like the analogy I'm using for the end of the plasma. The plasma universe was like opaque. Nothing could get through, no light could get through. When it dropped below that temperature of 3000 degrees, suddenly it became transparent. The photons of light could escape. And then we had the cosmic background radiation. So if the steady state theory was true and everything was the same all the time, then you wouldn't have this change in temperature. You wouldn't have this change from being opaque to being transparent. And therefore you wouldn't have the cosmic background radiation. But we do have the cosmic background radiation because it did happen. So that is very strong evidence for Big Bang. And really the steady state theory couldn't explain that away. So the existence of the black body background, which is just the cosmic background radiation, ruled out steady state actually being a plausible theory. So more evidence of the Big Bang. So we talked about cosmic background radiation, the abundance of hydrogen and helium, and eventually Hubble's law of redshift showed that universes were expanding away from one another. And they weren't being replaced, okay? So we do have big empty spaces in the universe. We don't have this uniform distribution of everything like steady state matter suggests would have been the case. So remember, cosmic background radiation was discovered by accident in 1965 by Penzias and Wilson, and they were using this horn antenna to pick up low-level noises in space. They weren't looking for the cosmic background radiation. This horn shape of the transmitter is good for the work they're trying to do, but also very nice for pigeons. The pigeons were roosting in there, and there was a lot of pigeon dropping, so they thought, this hiss that they kept hearing was caused by the pigeons. They cleaned it, and they still heard this hiss. And then they took it to somebody else who said, look, I think you've actually discovered this. Then we used the Kobe satellite to map the cosmic background radiation. And we saw these inconsistencies in the cosmic background radiation, these tiny temperature differences that was further supported by the WMAP satellite in 2003. And when we figured out that there were these tiny differences, that gave us really good evidence that gravity could get to work to pull these tiny differences, magnify those differences, and start creating more interesting things like stars. So this was huge boost for the theory of Big Bang. The abundance of hydrogen and helium we talked about last year, but I'm going to be a little bit more. I'm going to just add another layer of complexity to what we know. So there's a term called nucleosynthesis, and it refers to the formation of heavier elements, so the atomic nuclei with many protons and neutrons, from the fusion of lighter elements. So we've talked about nuclear fusion before. The Big Bang theory predicts that the early universe was a very hot place. 1 second after the Big Bang, the temperature of the universe was roughly 10 billion degrees and was filled with a sea of neutrons, protons, and electrons. As the universe cooled, the neutrons either decayed into protons and electrons or combined with protons to make deuterium, which is an isotope of hydrogen. Now remember, isotopes are interesting. And what is an isotope? Well, we know that a proton, the number of protons in an atom, determines what element is there. So if I have one proton in an atom, I have hydrogen. If I have two protons in an atom, I have helium. If I have 3 protons in an atom, I have lithium. But if I change the number of neutrons, it doesn't affect the element, but it becomes an isotope. It becomes a slightly different version of the same element. Okay, so we'll talk about that in a little second. During the first 3 minutes of the universe, most of the deuterium combined to make helium. Trace amounts of lithium were also produced in this time, and this process of light element formation in the early universe is called Big Bang nucleosynthesis. So these are the 3 isotopes of hydrogen. What I hope you notice is every single one of them has 1 proton. That's because hydrogen has to have 1 proton. If it had any other number, if it had none, it wouldn't be an element. If it had 2, it would be helium. If it had 3, lithium. But you'll notice that the number of neutrons changes in the nucleus. So the first one is protium with no neutron. The second one, which we're talking about, is deuterium, which has 1 neutron. And we have tritium, which has 2 neutrons. So these were important. The formation of deuterium, the neutron forming with the proton in the early universe, was really important. And these would combine with another deuterium isotope to create helium. The last bit of evidence that we've looked at in length, so I won't go over it for much longer, was the redshift. So Doppler had found that objects moving away from the Earth gave off longer wavelengths of light, and they looked red, appeared red to us. And if things were moving towards the Earth, they'd have a shorter wavelength of light and appear blue. And what he discovered was that everything in the galaxy, in the universe, was redshifted from us. It was moving away. And that proved the expansion of the universe, and it wasn't happening at a uniform rate. The further away you get from us, the faster the universe is expanding, like an explosion. And how do we know about this? Well, we had looked at the Doppler effect as well. So light waves to explain the movement of galaxies is important, but we can also use sound waves to make that example a little bit more realistic or put into context. The example we used was the Doppler effect with sound waves, which is the upward shift in frequency of a moving source of waves towards whom the observer is moving towards, and an apparent downward shift in frequency from whom the source of waves is receding from an observer. So it's the same principles that we use. So we've done this a lot, but it's nice to remember. And we use these principles to help explain redshift. Okay, thank you. Hamish has told us that dragonflies have 6 legs, but they cannot walk. How interesting is that? Thank you, guys.